Hello everyone, I am Sunanta from SNS College of Technology, Department of Mathematics. As the continuation of the lecture series in the topic numerical solutions to ordinary differential equation, we are going to see Euler's method in this lecture video series. So before getting to the video, first let us see the introduction to the Euler's method. So here this Euler's method is a first order numerical method for approximating the solution of an ordinary differential equation. So this method uses slopes at points to estimate the solution at the next point. Iteratively stepping forward to approximate the solution of over an interval. Here this method approximates the solution by taking small steps along the tangent line at each point. First, the formula for this Euler series method is yn plus 1 is equal to yn plus h f of xn comma yn, where this yn plus 1 will be the next iterative and yn is the given initial value and h is the small single step, that is iterative, or which can be said as a steep size. So steep size can be denoted as h, and this f of xn comma yn will be the given initial value problem. Here the process for this Euler's method is, first we will start with an initial condition, that is we will be given with an x0 and y0 value. We will consider that as an initial step. Next is choosing the steep size. The steep size h can be found by x1 minus x0 and x2 minus x1. Similarly, on calculating these values we will get the h value. Next is we will apply the h value, f of x0 and y0 value in the given problem, and we will substitute that in the given formula, which in turns give the solution of the given problem. So next we are going to see the accuracy of this Euler's method. So this Euler's method, as we have seen already, this Euler's method is a first order method. So meaning is the local truncation error is proportional to h square, that is the square of the steep size. This means that accuracy of the approximation increases as the steep size decreases. Next, limitations. So while simple to implementation, Euler's method can accumulate errors, especially at large steep sizes. For example, if we have the h value to be equal to 2, 3, 4, 5 and all, this error will be large. When we take the h value very small, for example 0.1, 0.001 like that, then the errors value will be very much comparatively lesser, 2 of h is equal to 2, 3 and all. More the sophisticated numerical methods, Runge-Kutta method can often be used to get the accuracy of this. So next, coming to the stability of the Euler's method, the choice of steep size can also affect the stability of the solution. So if the steep size is too large, then the numerical solution may diverge from the true solution. Next is error analysis. So the local truncation error can be given by OH square. Next, global error can be given by OH into OH, which is the first order method. Next, improving the accuracy. So to improve accuracy, we can take the h value to be smaller, or otherwise we can use higher order methods like Runge-Kutta method and all to find the approximate solution or a more accurate solution. So when coming to see the advantage and disadvantage of this method, we can see this method is a simple and easiest method to implement. Next, it gives quick result comparing to the even Taylor's method. So in Taylor's method, we need to find the value of the derivatives. Next on we have to substitute the initial problems, whereas when we come to the Euler's method, we can directly substitute the h value and initial values, we'll get the solution. So next is disadvantage. So this method is very low accurate. Next is requires a small h value. So when the h value is small, the answer will be approximate. So when we take the h value as large, then it will be a disadvantage for us. Now we can see a problem based on this method. Before getting to the problem, let us see the formula for Euler's method. So here the Euler's formula is yn plus 1 is equal to yn plus h into f of xn comma yn, where this n values ranges from 1 to etc. So now let us see a problem on Euler's series method. So using Euler's method, we are going to find the value of y of 0.2 for the given differential equation or an initial value problem. Dy by dx is equal to log of x plus y for y of 0 is equal to 2 at h is equal to 0.2. Now as we see in the problem, we have our x naught value is equal to 0 and our y naught value is equal to 2, and our f of x comma y is equal to log of x plus y. Now we are going to apply all these in our formula, which is yn plus 1 is equal to yn plus f of h into f of xn comma yn. Here we are going to apply n is equal to 0 since our y naught value is known. So therefore y1 is equal to y naught plus h into f of x naught comma y naught. Here the y naught value is 2. So 2 plus our h value is equal to 0.2 as given in the problem. Next f of x naught value is 0 and y naught value is 2. As we substitute the values, we will get 2 plus 0.2 into our f of x comma y is equal to log of x plus y. So log of x value is 0 and y value is 2. So we get 2 plus 0.2 into log of 2. So as the log 2 value is equal to 0.3010, we can write the answer of this problem as 2.0602. Our y1 value is equal to 2.0602 from the Euler's method for x1 is equal to 0.2. Thank you.